Okay, in this video I'm going to talk about the tangent length to the incircle and the excircle of a triangle. So basically we have a triangle, and the incircle is the circle that is inscribed in this triangle. That means that it touches all sides. And then we have an excircle. So like every triangle has 3 excircles which touches the same lines of the triangle, but so one touches one side and the extensions of 2 other sides. So like basically this is an excircle, and there are 2 other excircles like that, here and here, but we don't need it now. We need only one excircle in this theorem. Okay, so basically the theorem states that the tangent length from the vertex, so basically this length, of course it's equal to this length, is equal to this length. So the tangent from one vertex to the tangency points of the incircle is equal to the tangent from the other vertex to the excircle. So these 2 segments are equal to each other. So, and of course then this segment would be equal to this segment, which is so this segment is like basically this tangent from this vertex to the excircle would be equal to the tangent from this vertex to the incircle. So this OR is equal to this. Okay, so let's write this. So let's denote the triangle as ABC and the tangency points as well, we don't even need to denote the tangency points. Let's just denote this segment. So let's denote this by X. So okay, let's denote the tangency points. This would be TC, TA, and this is TB, and for the excircle this would be B prime. This would be TA prime, and this would be C prime. Okay, so and theorem, yeah, and so let's denote now. Let's denote now the X would be CTA, and it is also CTB, because the tangents from the same point, like 2 tangents from the same point to the same circle, are equal to each other. So these 2 are obviously equal to each other. And denote Y to be ATB and ATC, so the tangent from A to the incircle, ATB and ATC. This is Y, and then denote X prime to be the tangent point from C, the tangent from C to the excircle, so CTA prime the same as CTB prime. TB prime. So the tangent from C to the excircle, these two segments, and then Y prime we denote the tangent from A to the excircle. So A T C prime and the same as A TB prime, right? So this is Y. This is Y prime. This is Y. Segment is Y. And this is X prime. This is also X prime. And this is also Y prime. This is also Y. Right? So, and now the theorem states basically that that X is equal to Y prime and X prime is equal to Y. So these two are equal to each other, and so these two are equal to each other, and these two are equal to each other. Okay, so the proof is basically we notice that like with this notation, so the side AC can be represented in two ways. So AC on the one hand it's like it's CTB plus ATB, so CTB plus ATB, and this is equal to X plus Y prime no, X plus Y, not Y prime, X plus Y, because ATB is Y. Right, on the other hand, it is AC is equal to ATB prime plus CTB prime, right? So it's equal to ATB prime plus C. ATB prime plus C TB prime, which is so ATB prime is Y prime plus CTB prime. This is X prime. Right? So these two are equal to each other. So we write it separately. X plus Y is equal to Y prime plus X prime. So this is one equality, and another equality is that the external tangents, common tangents for the incircle and excircle. So basically we have that TA prime is equal to TC TC prime, and why they're equal. So this is basically like for any two circles. Like if you have two circles and we have common external tangents, then this segment is equal to this segment. And why is that? Is simply like if we continue extend these lines to the intersection, then basically this segment is okay. Let's denote like A, B, C, D, P. So we have like PC is equal to PD as the tangents to the first circle, and on the other hand we have PA is equal to PB as the tangents to the other circle, right? And when we subtract one from the other, we get that PA minus PC is equal to PB minus PB, and so this is equal to PA minus PC. This is equal to AC, and this is equal to BD, right? So then they're equal to each other. So the common tangents, the external tangents between two circles are equal to each other. Okay, so this we can remove. Okay, so that's why, so the TA prime and TC prime are two external tangents to the incircle and the excircle, therefore they're equal to each other, and so TA prime is equal to x plus x prime, and this is equal to y plus y prime, right? So in total we have two equalities. So let's write this separately. So x, okay, here is x plus x prime is equal to y plus y prime. So we have these two equalities, and from this we can conclude. So like if we subtract the first, like the second one from the first one, right, we get x plus y minus x plus x prime is equal to y prime plus x prime minus y plus y prime, right? We subtract the second one from the first one. So then x and x cancel each other, and y prime and y prime cancel each other, and we get y minus x prime is equal to x prime minus y, and we move x prime to the right side and y to the left side. We get 2y is equal to 2x prime, and therefore y is equal to x prime. So this is one of the equalities that y is equal to x prime. So this is one of the equalities that we needed to prove, and the other is simply, well, one way to do it is just to substitute x prime in the first equality. So x prime, we already know that this is the same as y. So again, this is the equality, x plus y is equal to y prime plus x prime. Now we substitute x prime with y, and we get x plus y is equal to y prime plus y. Y and y cancel each other, and we get x plus y. X is equal to y prime, which is the second equality that we needed to prove it. Another way to prove it would be again to subtract the second one from the first one, but not to subtract, but to I guess to sum these two equalities, right? Yeah, like if we sum these two equality, let's do it. So we would x plus y plus x prime is equal to y prime plus x prime plus y prime, right? So we added these two equalities, and now we see that the left side would be 2x plus x prime plus y, and the right side would be 2y prime plus x prime plus y, right? So x prime cancel each other, y cancel each other, and we get 2x is equal to 2y prime, or x is equal to y prime. And this is exactly what we need, the same equality as this. Yeah, so this is another way to obtain it. So yeah, so basically this concludes the proof.